Good afternoon. Can you hear me?
Yes, sir.
Yes.
Yes.
Okay,
Yeah.
thank you. I would really appreciate if some of you who have a camera can actually come with your face. I can so that I can have a sense that there is somebody listening instead of just seeing names and screens. So I really appreciate that. Thank you, Bradley. Thank you, David. Sorry, no camera. That's okay. Whoever has, please come on. Okay, so we are recording. Thank you. This is lecture 3. We are all snowed in, but that won't stop us from learning numerical methods. So last lecture, we were talking about random variables, and we discussed that there are discrete and continuous variables. Discrete are those that are countable in steps of 1, like using a whole number, like a coin toss or a roll of a dice or a number of events of something. Or number of objects. And continuous are those which are usually uncountable with infinite resolution, such as height, velocity, temperature, length, anything that is usually physical and doesn't have any set theoretical limit on whether it's discrete or continuous. We also saw, at least within discrete variables, what is called as the probability function, which is if you take uppercase X to be a random variable, which could denote the outcome of a dice roll, for example, lowercase x is a specific value of upper X. That is, it can assume values like 1, 2, 3, 4, 5, 6. So we say that the probability of X assuming a value of lowercase x as P of X equals X. The sum of all the possible outcomes must equal to 1. So we denote that by saying summation from I equals 1 to n, where n is the number of possible outcomes. So n is the number of possible outcomes. If you sum it over all the possible probabilities, that should add up to 1. For a dice, n is equal to 6, and the probability of each outcome is 1/6. So if you add 1/6 6 times, you're going to get 1. That's what it implies. Okay. And this will get more complicated as we do more, different random variables or how they interact with each other and so on. So for a dice, it's a really simple example. We also started seeing what is called as the cumulative probability function, which is saying f, uppercase F assumes a value of lowercase x, which is like saying the probability that the random variable has values that is up from 1 until xi. So if I say f is equal to, f of xi, I'm going to stop saying this aloud. I'm not going to say uppercase X anymore. I'm just going to say f of xi, denoting that the random variable assumes a value of xi. Okay, f of xi is the sum of the probabilities from 1 until xi. So you have to sum all the probabilities. And obviously, if you include all the possible values of xi from, let's say, 1, 2, 3, 4 up to 5 or whatever the upper limit is, all of them should add up to 1. So I took this figure from the book, figure 4.2. So in the upper graph here, if you see the value of 1, 2, 3, that is x, the random variable assumes values 1, 2, and 3. The probability of each are given to you. Probability of 1 is 1/2, probability of 2 is 1/3, probability of 3 is 1/6. But if you plot the cumulative probability until you reach the value of 1, between 0 and 1, or after 0, the cumulative probability is 0. After you reach 1, it jumps to 1/2, which is the probability of 1. Between 1 and 2, it stays constant at 1/2. And then at 2, you have to add 1/2 and 1/3. That gives you 5/6. So it jumps from 1/2 to 5/6. And then it stays at 5/6 until 3. And at 3, you add the last 1/6. So you get from 5/6, you go to 1. And beyond 3, if there is a value for the random variable, it just stays at 1. So cumulative probability is like a bookkeeping of the probabilities from the beginning till the last possible value of x. So it readily ascertains the percentiles. So if I ask you, where is the 50th percentile or the median value for this distribution, what would be your quick answer looking at the bottom graph? Where does this set of random variables reach 50% probability? Here's the scale from 0% to 100%. Where is this scale reaching 50%? Right? And 50% is reached at a value of 1. So 1 happens to be not only the first possible value, it also is the median, coincidentally. Do you see why it is the median? Elias? Good.
Yes.
Do you see why it is the median? Because it is the value at which the distribution hits 50%. If I ask you what would be the 95th percentile, that would be between 5, 6, and 1. So it would be something between 2 and 3. So the 95th percentile, it's not exactly in this resolution, but at least you would say it is between 2 and 3. Okay. All right. So this is where we kind of stopped last week. And one important quantity that we calculate for discrete variables is their expectation. Okay, expectation or expected value or mean value of the random variable x. Okay, so for example, in a dice roll, what is the expected value? What is the expected value? E would be summation I equals 1 to 6 xi times probability is always 1/6. So I'll just write it here. Okay, so this is going to be 1/6 times what is 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is how much? I think we did this last time, 3.5. So the expected value is 3.5. Okay. So let's see if I can pick an example from the text and we could do one before we move on to the next topic. All right, if you have the book with you, let's take wait, hold on. Okay. Wait. Sorry. I wanted a discrete variable problem. I don't want a continuous variable. Never mind. We'll do this later. Okay. So I had another example selected, but that's not for discrete variable. Okay. So the opposite of this, that is, we've been talking about discrete variables, right? What about continuous variables? How would you define probability for a continuous variable? That is, let me be clear. Let x be a continuous random variable, okay, whose value can be any between minus infinity to plus infinity. It basically is a real number that can take any possible value. Okay. How do we think about the probability of x assuming a specific value. That is, I'm talking about a statement that is, what is the chance that X has a value exactly equal to 1. Exactly is the keyword here. I'm not talking about 1.01 or 0.99. I'm talking about the value of X taking exactly equal to 1. Before we go into the theory and how this is mathematically constructed, what is your gut instinct on the continuous random variable assuming a very exact value with high precision? It's like asking, what is the chance that somebody's height is exactly 6 feet even, and 6 feet will remain as 6 feet no matter how fine you make the scale? What are the odds of that?
Like very, very close to 0.
It's very close to 0. It's you can even say for sure it's almost 0, because the chance that anything is exactly 6 even is almost nil, because the finer you make your measurement scale, you will reveal more decimal points. That's intuitively true, right? So how do we think about probability for continuous variables, which we know can't assume exact values? Why I stress on exact values is, for discrete variables, the value is indeed exact. The dice has a value of 1. It's printed on there. Even if it's not about the printing, there are 6 faces. You have to call them something. You call them 1, 2, 3, 4, 5, 6. That's how they take exact values or discrete values. Whereas continuous variables are not like that. So let's go back 2 lectures. Okay, in the very first lecture we talked about histogram, and then in the second lecture we did histogram. Okay, so what is a histogram? You take a continuous random variable like height or time or velocity or some quantity. Let's say we call this X. Okay. Then we divide this into bins. We have a lower limit and we have an upper limit, and then we have a midpoint. And then each bin is denoted with its midpoint. And then we have different bins. And each bin has what? Each bin has a certain number of objects or a frequency count, and we take that frequency count, we either use it as raw frequency, or we do what? We normalize it so that it is scaled from 0 to 1. So this can be normalized frequency. Okay, and this is X, the value of the continuous random variable. Okay, with me so far? Just recapping what we did last lecture. David, are we okay? Good. Okay. So if you take any particular window, okay. So let me ask this question. I'll pose a question and then try to answer it. Okay. What is the chance that X assumes a value between X lower and X upper? That is, I just drew it for the first bin. X lower can be 0, X upper can be 20, like in the example we did. And if I ask you the question, what is the chance or odds that if you randomly choose a value from this data set, X lower or the value of X will fall between X lower and X upper? What will be your gut or quick answer for that?
The probability of that bin.
The probability of that bin, or in other words, the frequency count of that bin, or the normalized frequency of that bin. This would be the chance. This would be the chance or the probability that X assumes a value in this bin. It's true for any bin. If what is a bin? It's basically saying X has a value between the lower and upper, and the chance is equal to the normalized frequency, is equal to the normalized frequency count of that bin. Are you with me so far? Okay. Now you tell me what will happen, or what is the relative effect of making this bin wider or shorter. If I make the bin very wider, let's say, for example, I make this first bin so wide that it effectively is equal to the length of, or the width of 3 bins put together, will it make the frequency go up or go down? If I take this, I'll draw it with a different line, okay, different colored line. So if I define a new bin, which starts here and goes up to here, and I count this and the third bin, or the third frequency, add them all together, and I draw something that looks like this, does it make it more probable or less probable? What is the chance that X can fall between XL and the new XL? I'll call this new XL. What is the chance of X falling between XL and, sorry, X upper, new X upper? What is the chance of that? It would still be this frequency in normalized terms. Does it, right? So whatever this new frequency is divided by the total, which still remains the same. Am I making the point that if you make the bin width wider, it will look artificially that the probability went up? Yes, no? Sandy Pond, I see you nodding. Okay. What will happen if I do the opposite? What will happen if I take a bin and define something that is narrower than the first bin? If I make it narrower, okay, then it will look like, sorry, it won't look like this. I'm basically going to take the first bin and split that into, let's say, half a bin, so that I get 2 bins wherever the first bin used to stand. Then it will look like the probability went down. That is, the chance of X taking a value in a narrow range is small. The chance of X taking a value in a wider range is larger. Or in other words, the probability of X assuming a certain value, or the probability of X assuming a value in a certain range, is also dependent on the width of the range. If you choose a very narrow width, it will look like it is artificially 0. If you take a very wide range, it will look like it's artificially high. Would you agree with that? So the probabilities that we have to think, first observation is the chance or probability of X assuming a certain value, or X assuming a value in a certain range, actually scales with the width of the range. You make this range smaller, make it smaller, the probability will go to 0. Make it larger, the probability will scale with it. You make it larger and larger, it will look like it's almost certain that it will be something. It's like asking, what is the probability that the height of a person will fall between 4 feet and 7 feet? What would you say? 100%, right? You don't even have to think. Anybody will have a height between 4 feet and 7 feet. An adult is most likely to have a height between 4 to 7 feet, although there may be some people whose height is not. They may be very small in number, but maybe 99% is chance that it is between 4 and 7 feet. Okay, so if you make the width wider, the probability scales with it. If you make it narrower, the probability will go to 0. If you make the width, make it 0, meaning chance of X assuming an exact value is make it 0, or that is make the width 0, the probability is also 0. Did we agree on that when we started? The chance of height having an exact value of 5 foot is almost not almost small. That's exactly what we are talking about here. So from this discussion, what can you conclude? How to express probability then if it scales with the width of the interval of the width of your histogram? If it scales with the width, shouldn't we define probability also factoring in the width of the interval? That is, all right, draw with this. So if you have a histogram, okay, let's say you have a histogram, you constructed the data. I don't really know what widths you used. I just assume that it's something. It may or may not be the same choice that I may make. You have provided me a histogram, okay? What I can do is I can think of a function. So what is a histogram? This is the graphical representation. So here is the normalized frequency count versus value of the random variable. So if I tabulate it, it will be x versus f, or frequency normalized. So it will be like 0.0. When I say x, I'm talking about midpoints. We're talking about midpoints. So for each value of x, there is going to be a frequency value. I'll call it f1, x2, f2, x3, f3, and so on and so forth. Okay, you have provided me this data. You didn't tell me what your bin width were, how you got the original data, how you did the binning. You didn't give me any details. What I can do is I can take this and fit a function. Although we haven't seen curve fitting in this course, are you all at least heard of that term curve fitting, fitting a function to a data set? Heard of that before? Yes, no, linear regression, something you've done in your lab courses. Okay, so let's say you fit a function and we'll call this function f of x. A function f of x. Okay, from f of x, how can I extract probability? That's what I'm going to talk about. Fit a function f of x to the histogram. Okay, how to get the probability that x takes on a certain value from f of x? That's the question. Now answer this for me. What is the chance that x takes a value exactly equal to, let's say, 1? What's the chance? Exactly 1, x equals 1. That would be 0. Others, are you with me? I haven't heard anybody talk today. Is it okay, followable? Can I at least get some reactions, raise hands to actually tell me that this is working? Otherwise, I'll be, I don't know, it'll be frustrating to find out it didn't work after the lecture is over. Ryan, thank you. David, thank you. Chase, Nicholas, Zane, Sean, Thomas, David. Okay, good. At least some people are saying yes. That's good. Okay, so the chance that x takes a value exactly is 0. Then the probability that x takes a value takes a value between, let's say, 1 and 3. 1 and 3. The probability that x takes a value between 1 and 3 should scale with the width, which is 3 minus 1. Okay, with I'll call it delta x, with delta x, which is 3 minus 1. The probability that x takes the value between, let's say, 0 and 4 should scale with the width delta x equal to 4 minus 0. Would you agree? It should scale with the width, right? So if I make the width very small, in mathematical terms, we call it infinitesimally small, then the width, then the probability should be proportional to dx. Can I say that? If I make the width really tiny, whatever the tiny width is, it should still be proportional to dx. Okay. Somebody's entering the class. Okay. Okay. So now, coming back to this histogram, I fit a function, right? Remember, what is a function? It's basically a replacement of the data. It's like saying I have a curve that passes through all these points and reaches roughly these points and can replace this data set. So I can draw a curve which sort of replaces the data set. And once I draw the curve, I can get rid of the histogram that is underneath. That's what a curve fit is. You can get rid of the data. You can just have one function that summarizes the data, and we'll see more of that. Okay, so I'll draw that curve here separately without that underlying data, and I have my infinitesimal width dx. Okay. Okay, dx. All right. Now I'm going to say the chance or the probability that x lies between this very small sliver of x values is f of x times dx. The probability is equal to f of x dx. That is, I'll write some text here. The probability that x lies between the probability that x assumes a value in the range with width dx is given by f of x dx. Do you agree with this statement? Because if you do, you buy the idea of what is a probability density function, which is you take a density f of x and you multiply that by the width to get the probability. This is an important step. If this doesn't land, please tell me. I'll find another way to tell this or narrate this. This is a density. That is, this function is a density. You multiply the density with the volume, which is in this case a linear dimension, so it's just length. So density times volume gives you probability. Because the histogram measures the normalized count. The count divided by the frequency or the width of the interval gets you the histogram f of x. So the f of x multiplied by an arbitrary width should give you the probability back. That's the whole idea of a probability density function. Anybody wants to say something, articulate the same thing in their own words, just to make sure we are all on the same page? Feel free to explain this to yourself and to others based on what you understood. Okay. Since nobody is talking, I'll try this again. So probability density function f of x. Okay. It is a mathematical representation of histograms or histogram normalized by the bin width so that it doesn't depend on any specific way the histogram is constructed. Okay, so f of x times dx represents the probability of x lying between x and x plus dx. Okay, so if let's say 0 less than x less than 10, x takes values between 0 to 10. X is such a random variable whose value varies between, let's say it takes values between 0 to 9, which is like 0 to 8, or the height of humans. Okay, 8 feet. I don't know if anybody is taller than 8 feet. F of x, or what is the chance? What is the chance of x greater than 5? Or another way of saying that is 5 less than x less than 8. How will you represent it? If this here, you have a curve, okay, let's say it started at 0 and almost goes to 0 at 8 feet. If this is f of x dx, this probability or this area under the curve, Bradley is saying something. Just 1 second, Bradley. So this is f of x dx, the area under the curve between x and or in a trapezium of width dx. What if I want between 5 to 8? What is the area under the curve between 5 and 8? So the function f of x, you mean to say lowercase f of x, is a curve of the histogram and the bin width is the value dx. To find the probability, you multiply f of x and dx. Perfect. That's what we do, except we use lowercase f. Otherwise, you're spot on. So if I want the probability that x will be between 5 and 8, what do I do? In literal terms, I am calculating the area under the curve between 5 and 8. In mathematical terms, how is it represented? Area under the curve, if I say between 5 and 8, even if you didn't know probability, what do you know about integration to tell me?
You just integrate from 5 to 8.
5, correct, thank you. You integrate between 5 to 8, f of x dx. That's it. So this f of x probability density function is a compact representation of the frequency content, such that if you just sum it between any two variables or any two limits, you can get how much of the data is contained between those two limits. It can be between 5 to 8, it can be between 0 to 8, it can be between 0 to 5, any combination. Okay, so if that is the case, let's play 20 questions. Okay, so you are going to answer me what is, let's say, 1 second, I need to define the question. If x varies between, let's say, minus infinity to plus infinity, that is, the possible values of x range between 0 to infinity, tell me the value of minus infinity to infinity or plus infinity f of x dx. You don't have to even know what is f of x, but you can tell me what this is. Sum of all the outcomes is 1. So in this case, if all possible values of x are between minus infinity and plus infinity, what percentage of the probability is contained under that curve?
100%.
100%. Perfect. So it gets you 100%, or the sum of it should add up to 1. Okay. So if this is the case, okay, what is the chance that x has a value between, we'll say, 1 and 4? That would be simply the same thing, except we'll change the limits between 1, 1 and 4. 1 and 4. So if I tell you what f of x is, that is, if I give you a function that represents f of x, a mathematical function, an algebraic function, you can do the integration to figure out what this probability should be or will be. Okay, so evaluating probabilities in this case comes down to evaluating integrals. Previously, in discrete variables, it was evaluating summations. Here, it is evaluating integrals. Okay, all right. Let's add one more concept and then we'll pick an example. Cumulative probability density function. We'll call it f of x. Okay, probability density function, cumulative probability density function. So f of x is defined as whatever possible values that this random variable assumes from minus infinity until x of f of x dx. So if the probability density function looks like this, the cumulative density function, let's say this is minus infinity, this is plus infinity. The cumulative density function at minus infinity, what will be its value? Look at this function. Help me construct this. The cumulative density function f at minus infinity will be what? Will be. So if I put the upper limit to be minus infinity and integrate from minus infinity to minus infinity of any function, what am I going to get?
0.
0. Right. Thank you. So that's going to be 0. So it starts at 0. Okay. Starts at 0. And as it reaches a peak, and let's assume this is the, let's assume this value is like 0.5, so that this would be the median. It would reach the median, okay, 0.5. And then as you go beyond, so this means the 50% of the distribution is to the left of this line, 50% is to the right of this line. Okay, that's what median is. So it attains 50% at the median value, continues to increase, and then reaches 1 at this limit. So if you were to write that, what would be f of plus infinity? That would be all possible values, which is 1. Okay, so the same thing we talked about. We talked about probability function. We talked about cumulative probability function for discrete variables. Same idea carries over to continuous variables, where we talk about probability density function. we talk about cumulative probability density function. Okay, hang with me for one more second. We'll just also see expectation and then we'll do an example. Okay, so expected value or mean value of a variable, of a continuous variable, that would be, we'll call it x, and we'll put this between a square bracket to denote its average, is minus infinity to plus infinity x times f of x dx. So this is the expected or mean value, and depending on what type of function this f of x is, depending on what the okay, I'll write it here. Depending on the form of f of x, depending on the actual range of values assumed by x, not always, it will be between minus infinity to plus infinity. The integral may be evaluated to obtain the average or mean value of x. Okay. Now let me pick an example. All right, this is, I think, a fairly easy example to start with. Problem 4 from the text, chapter 4, page 131. Problem 4. I'll copy paste the problem here. Problem 4, chapter 4, problem 4, page 131. So we have a random variable. It's defined as this function here. Okay, we want to first plot this distribution function. Okay, how to, this is distribution, not cumulative distribution. This is the actual distribution. So let me see here. Let me make some annotations, okay, so that you can try this on your sheet of paper. Firstly, below 0, this probability is 0. Wait, this is the cumulative probability. That's why it varies between. Oh, no, this, okay, never mind. Yeah, so this is below 0. This function is 0, and above x, it is also just 1. Okay, so the graph will look something like this. So if you start at 0 and you map 3, okay, up after 3, at 3 and after 3, it's just going to be 1, and below 0, it's just going to be at 0. Between 0 to 1, it is equal to x divided by 2. Between 0 to 1, it's going to be x divided by 2. So at the value of 0, it's 0. At the value of 1, it's going to be what? 1/2. And then we draw a straight line. With me so far? And between 1 and 2, it has a constant value of 2/3. So from here, it jumps to 2/3. Okay, I'm going to use a different color. And it stays at 2/3 until 2. And between 2 and 3, it stays at 11 divided by 12, or I don't know, 11 twelfths. 11 twelfths is much closer to 1, so it should be somewhere here. So this is x divided by 2. This is 2/3. This is 11 twelfths. And beyond 11 twelfths, I need to redraw this. Beyond 3, or yeah, beyond 3, it just stays at 1. Okay, so that's our distribution function. This is part A. Are you okay with this? Are you able to walk with me on this logic flow? Is something contradictory?
I have a question.
Yes, please.
I don't understand what's on the x-axis and what's on the y-axis.
So x-axis is this x value, okay, the value assumed by x, and y-axis will be f of x, this function that we are plotting.
Is it the cumulative probability density function or the other one?
From how it looks like, it is the cumulative density function, but the book uses the word distribution function. If I were writing this problem statement, I would add the word cumulative to make it explicit. But looking at the function and the way it stays at 1 beyond x equals 3, this is the cumulative density function.
Thank you.
Okay. I'm sticking my neck out and contradicting the book here. They should have added the word cumulative here to keep it clear. All right, so now we have the cumulative distribution function. Let's answer part B. What is the probability that x takes values which are greater than 1/2? So here is 1/2. Okay, here is 1/2. The value of x, or 1/2 is reached by the time x reaches the value 1. What is the probability that x is greater than 1/2? Or what is the probability of x assuming all these values? That's the question.
It'd be the
And-
integral from 0 to, well, my bad. Never mind.
No. You're on the thinking is right. Instead of integral, think in terms of summation. I'm going to write a clue here. Okay, I'm going to write something that could hopefully help. If you want to know what is the probability that x takes some value that is intermediate, let's say it's between x1 and x2, okay, that would be f of x2, f of x equals x2 minus f of x equals x1. Why is this correct, or why is this true? What is f of x2? Think about it independently. It is the values of all possible. It is all possible values from the beginning to x2. This is all possible values from the beginning until x1. So if you want between x1 and x2, you just take these two values, subtract the if you take the cumulative probability from x2, subtract the value from x1, and you'll be left with whatever is intermediate. Okay, so in this case, if I want probability, P of x greater than 1/2, okay, what would I do? I would write the function from x running x equals x equals 3 minus the function running from x equals 1. That would be 1 minus 1/2 or 50%. You can think of it in another way also. This is 1 minus 1/2, or this is 1/2. You can think about it in another way, which is the value of 1/2. Okay. Oh, wait. Sorry. This is mistaken. Sorry. This must be, okay, let me rewrite this. Probability of x greater than 1/2. Okay. Can I write this probability of 1 minus probability of x less than or equal to 1/2? Can I write it this way? By x greater than half, we are asking for anything half or more. I'm saying that must be the total minus anything that's half or less than half. Is that okay to write? Okay. So what is the probability? So this will be 1 minus, what is the probability of x less than 1/2? How is that defined? Oops, sorry. What is f of x equals x? That is probability of x less than or equal to x. So this is nothing but 1 minus f of x, f of x equal to half, which is 1 minus what should I write? I'll give you a minute to think here.
1/4.
1 minus 1 by 2 divided by 2, which is 1 minus 1/4 equal to 3/4. Take a minute, make sure you understand this, and please ask me if I want to, if we need to talk about this again, or I can go over it more slowly. Take a minute. Is everybody okay with this? Like, are you able to agree with me? Something not clear? Bradley? Okay, thank you. I didn't understand how you got 1/4. I'll come to that. Okay, let's see. All right. Okay, so all right, let's go over this again. This is what we want. What are the chances that x will take values more than half? That is like saying, what are the chances that x will take less than half, or 1 minus p less than or x less than half? Do you understand this step? Okay. Now this particular value is the probability of x assuming values from 0 until half, or from the beginning until half. That is precisely the definition of cumulative density function. That is like evaluating the density at x equals half. So this is exactly equal to this. So if I want the value of cumulative density at x equals half, I just take this function wherever half is placed, which is between 0 to 1, and I have to substitute half in terms of x. So that is 1/2 divided by half, which is 1/4. So 1 minus 1/4 is 3/4. So the answer is 3/4. The chance that x will take values that are greater than 1/2 is 3/4. You can also look at it very intuitively here. If you look at this graph here, this is 1/2. Okay, which means this is the median. 1 is the median. And between 0 to 1, the probability scales linearly. So if you take half the interval, you will get half of that probability. So this is median, means this is 1/2, or 1/2 means that is median. And then this must be 1/4. So 1/2 plus 1/4 is 3/4, which is what we get here. It's not always about doing the algebra or math by lot of steps. You should be able to think intuitively. Okay, so here is one way to, once you get the answer, take a moment, reconcile it with what you can intuitively say from the graph. Okay, does that make sense? All right, thank you. Okay, let's answer the next part. What is the probability that x takes values between 2 and 4? What is the probability? So this is P4 continued. What is the probability? Oops. Probability that 2 less than x less than or equal to 4. This would be the function at x equals 4 minus the function at x equals 2. Sorry, the cumulative function at 4 minus the cumulative function at 2, which is, what is the cumulative function at 4? 1 minus what is the cumulative function at 2? That would be 11 by 12. 11 by 12, sorry, 11 by 12, which is 1/12. Look at this. Tell me if it makes sense to you and you agree with, if the logic seems correct to you.
I have a question.
Yes.
How would this thing look in terms of that 1 minus probability thing we just did on the previous slide?
Okay, so here in this slide, you are asked for everything that is to the right of half. Okay, it's kind of unbounded. So you say I will turn it into a problem which is bounded between 0 to half and 1, which is the sum of all the outcomes. Here you are already given a bounded range. It's not to your advantage to convert it into an unbounded problem. So if you have this between 2 to 4, the negation of that set would be, if I were to do it that way, p less than x less than or equal to 4, this will be equal to, I have to count everything to the left of 2 and everything to the right of 4, which is function of x equals 2. Okay, and it won't work out because you're trying to include what is in between. You're not trying to exclude it. If you're trying to exclude it, yeah, then it would make sense. So it won't be a useful way to write like this in this case.
Okay, I understand.
Okay, let's try the third problem. Oops, sorry. What is probability of x less than 3, which is the function x equal to 3? If it were sorry, function probability of x less than 3. So up and until 3, the probability density has, oh, this is easy. I won't tell the answer. I'll give you a minute. You think and tell me. What is the probability that x is less than 3? You just look at this function, you can tell me quickly. If x equal to 3, the probability becomes basically, wait. Yeah. If you're talking about x greater than 3, then the probability is 100%. Anything that is even slightly less than 3 belongs to the previous interval until which the probability is 11/12. So this is directly 11 divided by 12 from the table. No calculation needed. Everything until 3, which is x less than 3, is 11/12. That's what this statement literally means. F of x equal to 11/12 as long as x remains less than 3, which is what we want. So it's 11/12. Did that make sense?
Isn't that just for between 2 and 3 though?
That is the value of the density function between 2 and 3. What is density function? It includes everything from the beginning up until that point. So if you keep adding it up, it only will go up to 1. It can't be lower than, so anything, whatever you have here or whatever you have 2/3 cannot be lower than x by 2. 11/12 cannot be less than 2/3. 1 cannot be less than 11/12. So if you are interested in everything up to 3, but not including 3, that is directly this 11/12 here. Let's try part E. What is the probability that x equal to 1? Exactly equal to 1, not less than, not more than, exactly equal to 1. 2/3. Okay, we have an answer, 2/3. So I'll give you two choices. One of them is 2/3. The other would be 2/3 minus 1/2. What do you think? If you look at the function here, until 1, but not including 1, the probability is approaching 1/2. At x equal to 1, it jumps from 1/2 to 2/3. If you include 1, you have to look at this 2/3 and not the previous one. So if you are interested in only in the outcome of 1, not the one below, not the one above, you have to take 2/3, but you should also remove the contributions of everything up to 1. So that's why I think 2/3 minus 1/2 is the correct answer and not just 2/3. So there were some questions in the chat that I'm just seeing. Madison, do you still have that question? What is f representing in 1 minus f of x equals half?
I just don't get where the number is coming from. Like you have, like in this part, you have x equals 4 next to the f. I just don't get which numbers you're using.
Okay, so when I talk about f of x equals 4, this is f of x. That is, in the book they use the lower script. I'm using the uppercase. So if you want, I can change that. Okay, I want to know what is the probability that x lies between 2 to 4, which I can define as f all the way from 0 to 4 minus f from 0 to 2. Do you understand this part? Is that making sense? This part alone. We'll come to the next step in a second. You're not sure how this came about? I can explain.
Yeah, that's the part I'm confused about.
Okay, this goes back to, for those who are not sure, f equal to x is defined as probability of x less than or equal to x. This is the definition of cumulative density function. Definition of cumulative probability function. Okay, that is cumulative probability of a certain value is defined as all the sum of all the probabilities until that value. That's what this symbol means. Until, from 0 until x, or minus infinity until x. So when we write probability that x assume values between 2 to 4, that's like asking, I'll draw it to make it more visual. So if you have, let's say, discrete values here. Okay, so let's say this is 2, this is 4. If I say f of 2, that represents everything to the left of 2. That represents everything to the left of 2. If I say f of 4, that represents everything to the left of 4. All the way here. So if I want between 2 and 4, I need to take the f of 4 and subtract it from the f of 2. That's what I meant, that the probability of x lying in between is written as f of 4 minus f of 2. Did that make better sense?
Yes, that makes sense.
So once you write this, then it's a matter of looking up this function from this table. So if your x is more than 4, you just write 1. If your x lies between 2 and 3, you write 11 divided by 12, and that gets you 1/12. Okay, by the same logic, if I want to know what's the probability that x is less than 3, I have to look at this function and see where the probability reaches 3, which is here 1. But if you are not including 3 itself, it is 11 by 12, which is what we got here. And for probability of x exactly equal to 1, if the cumulative, if the question were probability of x less than or equal to 1, this is equal to probability of x less than 1 plus the probability of x equal to 1. What is the probability of x less than or equal to 1? That would be 2/3, because you are here, x is included here, it's 2/3. What is the probability of x less than 1? You are not included here, but you are included in the previous bin where x is less than 1. So that will be 1/2. Okay, so you take 2/3 equal to 1/2 plus probability of what you want, which is x equal to 1. So you just rearrange and this becomes the answer. So Thomas, would you agree with me? It's 2/3 minus 1/2.
I have a question.
Yes.
When you're saying 1/2 and it says x over 2, why are you substituting the x with the 1? Like 1 over 2.
Right. So when you are thinking of a continuous function, you if you want to write x equals 1, okay, you can include that in the interval for calculation, but the probability itself is counted in the next bin. That's how I see it. So if I don't do that, there is no other way to calculate what is probability of x less than 1. How would you calculate it without substituting the value 1 itself here? Like when you say x is less than 1, you can get it, what it means theoretically is you can keep getting closer and closer to 1, but you are not exactly at 1. That except that exact value, you can keep getting closer and closer. But to evaluate the function, I need a value, which is why I take the value of 1. Otherwise, I don't know what other choice would work. If you tell me, or if you can think of something, yes, I would like to know, but I can't think of anything else. I'm serious. It's not like a sarcastic remark. I really can't think how else would I be able to calculate probability of x less than 1 other than substituting x lowercase x equal to 1 in this formula here. That made sense to me. That's why I did that. Okay. Yes. We have time for one more example. Are we good to move forward? We'll do one on continuous variable. Yes. Thomas, are you okay with 2/3 minus 1/2? I saw that answer in the chat. Yes.
I have a
Okay.
question.
Yes, please.
So what if we wanted to find the probability of x equals 2?
X equals 2 would be 11/12 minus 2/3.
So the 2/3 includes the x over 2. So x over 2 is added to 2/3.
2/3 does this interval, if you look here, 2/3 doesn't include x equals 2. 2 is included in this interval. So if you want probability of x equals 2, that would be 11/12 minus 2/3 by the same logic.
Okay, so 2/3 already includes the contribution of x over 2.
2/3 includes the contribution of x less than 2, not exactly 2, but it's less than 2, between 1 and 2, 1 included, but 2 not included.
Okay, I got it.
Yeah. Yeah, as you will see, this idea of probability and calculation of these probabilities is there are some very simple rules, and the rules will become apparent not by studying the definition or the bullet points. They'll become apparent by doing problems. That's why it's important to practice, make some mistakes, have a debate, and then we'll come to a consensus or a conclusion on what is the correct way. So these debates are the way to go. Okay. Don't feel shy about contradicting yourself or myself, and All right, let's do another problem. I want to pick something fairly. We'll try this one. Problem 5. Same page, problem 5. Okay, this is a problem of chapter 5, P5, page 130. Okay, suppose the random variable has a probability density function, continuous variable, which is cx cube between 0 to 1 and it's 0 otherwise. Firstly, what's the value of c? Okay. To get the value of c, invoke the idea of total probability or area under the curve adding up to 1. That would be integral minus infinity to infinity f of x dx equal to 1. Right? That's the property. And if you were to write it for this particular situation, that would be minus infinity to 0 of 0 dx, okay, plus oops, 0 to 1 of c x cube dx plus, you guessed it, 1 to infinity 1 to infinity of 0 dx, the all three integrals adding up to 1. I'm writing it out like this to show that the interval in the broadest or most general terms is minus infinity to infinity. But for a given random variable, it'll simplify quickly. So the first and third are not needed. So what you have is c times, you know the integral. You're going to do this on Thursday in your prerequisites quiz. 0 to 1 x cubed dx equal to 1, which means c is 4. Would you agree with me? C is 4. Yes, no? Okay, I am assuming that you do agree. And to get problem B, probability of 0.4 less than x less than 0.8, that would be what? If you say this, it means you have understood continuous random variables. Yes, you know this, come on.
Would we do an integral from 0.4 to 0.8 for f of x dx?
Absolutely, thank you. So we would just take an integral from 0.4 to 0.8, sorry, 0.8 f of x dx, I'll write that, okay, which is equal to 0.4 to 0.8. You know already c is equal to 4. So you have x cubed times 4 dx, which is x power 4. So this is 0.8 power 4 minus 0.4 power 4. You can evaluate and enter the actual number. I'll leave it to you. Is everybody okay with this? You're not feeling lost? You're okay, everyone? Yes, let's see. Kenzie, Brian, Chase, Mohammed, Carson, Daniel. Are we all okay? Jonathan? Okay, thank you. All right.
Professor, will you post these slides after class?
Absolutely, absolutely,
Okay,
absolutely. And thinking how convenient it is to write these things, I might just do slides from now on, like make the slides in class in front of you and instead of whiteboard, you know. All right, let's try one more example. We have 7 minutes. Okay.
Would you also post the recordings on Canvas?
I've been posting. If you look at the syllabus file, the table of course topics, not course topics, lecture schedule, a link will appear after each lecture. Go watch those videos. Let me make some money with YouTube, please.
Okay, thank you.
These are all 90-minute videos, so please watch them. Thank you. All right, problem 8. Problem 8. Wait, problem 8 is not very difficult. We don't have a lot of time. We'll do problem 8. Okay, at least something is better than nothing. Problem 8 almost is very similar to what we just did. First, the density function is given as an exponent between 0 to infinity. Below 0, it is just 0. So it's just a positive definite function. Find C. What is the probability that X assumes values that are greater than 2? That's the question. So to find C, to get C, we'll write integral. Can I just go 0 to infinity? I don't have to write it out from minus infinity. You'd be okay with that, right? 2x dx equal to 1. So then we'll have to write C is equal to 1 divided by the integral from 0 to infinity e power minus 2x dx, which again for your prerequisite quiz could appear on Thursday. What is this value? If I write that quickly, would you be confused? Would you be okay? You do get that the integral of this is 1/2, correct? Right? Yes, okay. Brian, thank you. Okay, so then we are asked the question, what is the probability that X takes values that are greater than 2, which would be integral 2 to infinity, sorry, would be 2 to infinity, C is already 2, e power minus 2x dx, which you can actually solve a little conveniently with the idea of density function, but that's okay. It's not that bad. 2 e power minus 2x divided by minus 2. That's the integral. And you have to evaluate this between infinity and 2. If you put infinity here, it's just going to be 0. If you put 2, that's going to be e power minus 4. So this is something like okay, maybe I'm going too fast on this. Okay, I'll have to evaluate this between 2 and infinity. Okay, the upper limit is 0. That is, if you substitute infinity, you're going to get 0. The lower limit will get you e power minus 4 and with a negative sign. So this whole thing is something like e power minus 4. That's the answer. The answer is okay. What does it tell you? What is the, if you just think about this function here, how will it look like? Or if you try graphing this function, it starts at 0. Okay, so if you put 0 here and the value of C is 2, you're going to start with 2. Okay, start with 2. From 2, it just rapidly decays and goes to 0. So if you are standing here at 2, okay, by the time it reaches 2, the probability of the values that are to the right of 2 is almost e power minus 4. E power minus 4, if you didn't realize, is a very, very small number. It's almost like an inconsequential number. You can think that most of the values of this function are already before 2, or if you do the calculation, they might be before about 1.5. After 1.5 itself, there might not be much left. It's mostly confined to 0 to 1.5. Okay, so the skill I want you to pick up here is, of course, to calculate these probabilities and do these integrals. But when you see a function, you should be able to visualize it, plot it, think about how fast the probability falls with the variable x, and also think about how the cumulative distribution function will look like. How soon will it plateau out? What value will it reach? Where will be the median? Where will be the mode? You should be able to think about these things intuitively. That's what I want you to master. Don't stop the problem when you just get a numerical answer and then you are done. Think a little bit about the form of the function, try visualizing it. You can almost take it for granted that in the exam, whatever function you are working with, there will be a section, part A or part B or something that says, draw a simple graph of this function. That question is almost certain to appear. Okay. Before we depart, any questions today?
I have a question about why here we can go from 0 to infinity, but not for the one before. Why did we do negative infinity to infinity for the question before this one? But
so in this, you should do it technically for every question. There's no doubt. Only thing is below 0, that is from minus infinity to 0, this function is given to be 0. I just saved one step by not writing it. That's all.
Okay, got it.
Yeah. Okay, so we'll stop here. We'll pick this up on Thursday. Please go through problems in chapter 4, which is what we have covered so far. On Thursday, I plan to do chapter 5, which is some specific types of distributions like Bernoulli, Poisson, normal distribution, and uniform distribution. And then we'll keep continuing. But so far, what we have done is chapter 2 and chapter 4. So please do end of chapter problems from those two from the statistics text. I don't know how many of you realized it. The first module statistics has its own text by Ross. I've given the link in the syllabus. Please download the chapters and follow the correct section numbers. Okay. Thank you. See you on Thursday. We have the prerequisites quiz if we return to class.
Have a good day.
Thank you.
You said the chapter 2 questions, right?
Chapter 2 and chapter 4.
Okay.
That's what we have covered so far. So please do the end of chapter problems. I would say minimum do 5 to 10 problems.
Okay.
Yeah.
Cool. Have a good one.
Thank you. See you Thursday.
And we need to do those problems before next class, right?
Yes, that would be helpful so that you reinforce the discussion today.
Okay. Thank you.
Thank you. Yeah. I'll post these slides.